We are finally done with Chapter 6, and we're going to move on to Chapter 7. The first section here is going to be called Power Functions. But first, I actually want to go back and look at the warm-up. One thing we have to kind of do as like a reminder is what is domain and range. So I'm going to go through some examples of how to do domain and range and how to write it, in case you've forgotten. So for the domain and range of graphs, we had this notation where we kind of used brackets or parentheses, and it kind of looks like an ordered pair. So I'm going to go through this with you. So for domain, that is the x values, looking from left to right on this graph. So you're kind of reading how far to the left can you go and how far to the right can you go on the x-axis, and from where the graph starts and where this graph ends. So we look at the left side and we kind of draw this line down, right? What point is this? That is at -2. And since there's a closed dot, we use a bracket like this. And we say -2, comma, go to the right, look down here, we are at the number 4. Again, closed dot, bracket. That was one way we learned how to do domain and range. Range, you're going to look at the lowest point on the y-axis now we're looking here. So if we go down to the bottom, and the lowest point we can go to look across for the graph is at -4. Again, these are all closed dots. In this case, we're going to use brackets, -4. And then we're going to go up 1, 2, 3, not stopping at 4, but we can keep going. 5, 6, 7. Looks like this number here would be 8. So the highest point we can go is 8, closed. And that's how you do domain and range. Hopefully it looks familiar. There was another way we could write this out. We could actually write the domain as saying it's from -2 less than or equal to x less than or equal to 4. And then with the range, we would say it was -4 less than or equal to y less than or equal to 8. Either one is fine. I think we're going to mostly be dealing with this kind of notation because I think it's a little easier. Let's go over to part C. Now we have this kind of wavy graph. Let's do the domain, which is the x values. The farthest left you can go actually hits the x-axis here at -3. Now there is an open circle there, so we have to use a parenthesis for -3. And then as we go to the right, going this direction, we can see that it ends down here, and the x value there is 1. Closed dot, so bracket. The range would be the lowest point, which this wave comes down, touches here and here. The same point, they're both closed, so -4 with a bracket. And then the highest it goes on the y-axis, remember we're going up, it would be 0. And this does include 0 here, even though it is not there. That's okay. We will include it. Now, it's a little different whenever you go to a chart. See, the domain and range here is actually, in my opinion, a lot easier to do. If we're going to do the domain here, we would just really just list out all the x values. That's all we have to do. We put a curly bracket, and we go through all the x values, say -2, -1, 0, 1, 2. If a number happens to repeat, you don't have to write it twice. The range, curly bracket, again, just go across. -4, -1, 2, 5, and 8. And that's how you do a domain and range with a table. A little different with the graph because it's a continuous line. We have a range of numbers we have to go. We go from left to right, top to, or bottom to top. Always go from the smallest number to the biggest number, in both cases for range and domain. Okay, now that we have that behind us, let's start 7.1, power functions. How can you identify a graph? By looking at the exponent. So we're going to be doing some higher exponents rather than just, mostly we've been doing x squared, and we're going to see what some other ones look like. So in general, we call these nth power functions, which just means that the power function, the power as an exponent is n. It could be any number. So we say f of x equals x to the n. They call this the nth power. It could be a number. It could be like the 5th power, the 7th power, whatever. Specifically, though, we'll only be looking at where n is positive. And we're only going to be looking at whole numbers, like integers. So we have three different types. We have the identity function. that is whenever the n value up there is 1. So we say f of x equals just x, or x to the first. It means the same thing. Squaring function, think of something that's being squared. So that's just going to be x squared. And then the next one, the last one that has a specific name is called the cubing function. Think about x cubed, which is a 3. So we're going to practice graphing some of these. X squared we are very familiar with. I'm going to go ahead and just square these numbers and see what we get here. And then we'll figure out the domain range. So negative 3 squared. So for instance, what I'm doing here is we're doing negative 3 squared. That gives you a positive 9. Don't forget that it's like technically in a parenthesis set, so it's like negative 3 times negative 3. Negative 2 squared would be 4. Negative 1 squared is 1. 0 times 0 is 0. 1 squared is 1. And we get the same thing, 4, 9. And then we can plot these points. Again, you should already know what this looks like. We've done this many times before. So negative 3, we're at 9. Negative 2 is 4. Negative 1 is 1. And then down to 0. And then same thing on the other side. So we should see the happy face parabola like we always do. We're so used to drawing parabolas by now. There we go. It's hard to draw on this thing. And then what we have now, I don't think we've ever talked about, is domain and range on something like this. Specifically a graph that goes on forever. These arrows mean that it keeps continually going up. And not only that, but it's also getting a little wider. So it starts out pretty kind of small here, but this is growing wider this way, going out. This is also getting wider. So like this kind of starts, leaving each other. They're separating as you go further out. So let's talk about the domain. The domain is, remember, the x value. So we're looking at, okay, well, how far out to the left would this graph go if we kept going forever? Would it ever reach a point where it would be like, okay, maybe like, negative 12. It would never be out here. Well, no, it would be out there at some point. This goes on forever. And if it's getting wider, which means it's going this direction, even if it's slowly, it's still going this way. Same thing with the other side here. This is getting wider. It's taking up more and more x values, right? 4, there's a point up here. 6, there'd be a point up there. 8, there'd be a point. You can keep going on here forever. So in this weird case where you have a graph going in both directions, left and right, getting wider, separating from each other, the domain here is infinity. And we use this sign here. So if you're ever going to do infinity, we use a parenthesis because we don't have an ending point. And we're going to say this is from negative infinity. It's kind of like a sideways 8 a little bit, to positive infinity. Another easy way to write this, I'm not sure if I showed you this before, but another easy way to write this would be all real numbers. It's the same thing as all real numbers. And there's a symbol for that, which is you draw 2 lines and then draw your R. This means all real numbers. All right, for the range, this is the y value. So I'm going to put the y-axis here. And it's the lowest point it goes down to. Oh, it does have a minimum here. The minimum is 0. So it actually does come down and touch 0. So I'm going to hit bracket 0. But again, if we go up, it goes on forever up here. It keeps extending in both directions, but it also keeps going up. So it does not have a restriction on how high it goes. We're going to use infinity. This one you cannot use the R because R just means everything's possible. In this particular case, everything works but negative numbers. It's not down here at all. Okay, let's try another one. We have x cubed, so now we're going to raise it to the 3rd power, which means we multiply it by itself 3 times. So if you're going to put this in the calculator, you can do that with a parentheses around it. So we're going to do negative 4 cubed. That means negative 4 times a negative 4 times a negative 4. So in this particular case, since there's 3 of these, you would multiply 2 of them and get a positive 16 times a negative 4. Then if you multiply these 2 together, you would actually get a negative number. So this is going to give us a negative 64. Well, as you can see, we're not going to be able to plot that point. But in this particular case, when we plug in a negative, we do get a negative. In the last one, we did not plug in a negative and get a negative. It became positive. All right, -3, if you cube that, whoops, put a 2 there. If you cube this number, you would get, wow. Let's just maybe redo that whole thing. There we go. That would give you a -27, because you'd be like 3 times 3 is 9, times 3 again is 27, and again you'll get your negative here. Again, can't plot that. -1 or -2 cubed, that would be 2 times 2 is 4 times 2, which is 8. We're going to get a -8. We can plot that. -2 is -8. So it's down here. -1, well, multiplying -1s multiple times is not going to change the number at all. It actually gives you -1. So -1 is -1. It's right here. 0 cubed, I don't think I have to write the cubed out every single time. That's going to be 0. And then we're going to get the same answers over here, but now these will stay positive. So we're going to get 1, 8, 27, and 64. So we can plot 2 of these. 1, 1, 2, 8. So I don't know if you noticed, but this one is increasing a lot faster. But it is still getting a little wider. So I'm going to draw this as it kind of looks like maybe a slight bit of an S, maybe kind of. It kind of goes like this. And it keeps getting wider. And then it goes like this. And it keeps getting wider. It might be harder to see here, but this does keep continuing to go out to the right here, which is pretty important. I guess this one goes out to the right. This one goes out to the left. So if you look at the domain here, it's going to continuously go to the right across the x-axis. It's going to go across the left, towards the left side of the x-axis. All the left numbers, all the right numbers, positive and negative. This is the same answer as before, -infinity to positive infinity. Or if you want to use the all real numbers symbol. The range here is a little different because it is now in the negatives, and it's continually going down in the negative values for the y-axis. It is also continually going up in the y values. So this one is the exact same answer as the domain. There is no real stopping point at all. It spreads out across the x and the y-axis. So whichever one you'd like to use there. All right, now we have a little question here. What are some similarities and differences between example 1 and 2? So I'm just going to talk about them instead of writing them out. One is something that's different is the range is different slightly, right? 0 to infinity, -infinity to 0 and infinity. The domain is the same. There's a similarity. They both include this first quadrant, right? They're both in this quadrant, but the other part of it is not in the same quadrant. So this one is in the third quadrant, and then this one back here is in the second quadrant. Maybe we should talk about quadrants. It goes around the circle. 1, 2, 3, 4. It's counterclockwise. So there's a couple different things. And you could also talk about the table and how, this one here kind of gives you the mirror image of the same numbers on both sides of the vertex here. We've talked about that before. This one's not the same. They have the same numbers, but some are on this one side as positive, the other ones are negative. This one doesn't have any negative numbers. There's a couple different things. We're going to summarize these different similarities in a little chart here, talking about the domains, the range, the quadrants, and what kind of symmetry they have. So believe it or not, we only did x to the third and x squared. However, if we were to go to x to the fourth, this would look very similar as far as the domain and range and quadrants, things like that. Everything is very similar. The numbers here would be a little different. Same thing with x cubed. If we would go to x to the 5th power or the 7th power or the 9th, they all look the same. Domain and range is the same. So this is kind of summarizing, no matter what number you have, whether it's n or is even or odd, they all look the same. So even would be like x squared, x to the 4th, x to the 6th. You can go up as high as you want. X cubed would be odd, x to the 5th, x to the 7th, and so on. All right, the domain is the same every time for the even ones, which we had. I'm just going to use the R symbol. Also, when it was odd, it was also the R symbol. When it's odd, we use the R, all real numbers. The range here when it's even, though, however, was from 0 to infinity. Quadrants, even, if you want to go back, you can check it out. Even is 1 and 2. Odd is 1 and 3. And then the symmetry that they have. So this is a little bit weird and different. We've talked about the symmetry of a parabola before, where we talked about the axis of symmetry, right? The line that where you draw right down the middle that would cut it in half. And so we would say this has a symmetry, at the y-axis right now. But the type of symmetry this is called is reflection, where it looks the same on one side as it does the other. It reflects across the axis. So the type of symmetry here would be a reflection. And since we're not really doing anything to this equation here, we're keeping it x squared, or x to the fourth. We're not adding any other numbers to it. It always looks like this. So it's a reflection over the y-axis. And that will always be the same thing. Reflection over the y-axis. The cubic function here, x cubed, does not have reflection. In other words, if you were to fold it any which way, these lines would not match up. Instead, it has something called rotational symmetry, where if you were to, say, put like your finger on this and think of this as like a spinner, if you were to spin this around, it would then match up. So pretend you take these two lines here and you're able to like spin this around, like you're playing twist or whatever. This goes around in a circle. If you were to twist this around, then they would line up. These two lines would match up. That is called rotational symmetry. So we'll call it rotation. And where do you rotate it at? Like where would you have to hold it? That would be at the origin, at 0, 0. And we'll call that rotation about the origin. And so whenever we do problems like this, you're basically just going to reflect back to this chart and use this as a reference, because all the answers are the same. Once you determine whether you have an even power or an odd power, you just look at this. That's it. Simple. We're almost done. All right, using the table in your calculator, graph the following power functions, make a rough sketch the function, and plot 3 points to show the directions. Okay, so I'll put this in Desmos to show you what it looks like, x to the fifth, but you should already know what it looks like. It's going to have that S shape on it. So let's put it in Desmos. That's desmos.com/calculator. I equals x to the fifth power. So that's what it looks like. And I can bring up a table. There we go. This one goes off pretty quick. When you get to number 2, it's already 32, which is pretty high up there. If you zoom out, you can see how it keeps extending. Okay. So the only points I can really plot is -1, 0, and +1. And we'll have to make a sketch of it. So we have 0, 0, 1, 1, -1, 1, and then we know that 2 is 32, so it's up there somewhere. So it's going to be very slight in how something, it's very curvy and flying up into the air there. But it has the same shape as I said it would from x cubed. It's going to have the same properties. So let's go ahead and go down here and check out some of the answers. What's the domain and range of this x to the fifth? Which, without even graphing it, we should have known what that would be. Odd powers, this is odd. Odd powers, you go back to the little table. Odd, just gonna use this. All real numbers, all real numbers. So domain and range is all real numbers. What kind of symmetry does the graph have? This has the rotational symmetry. Rotation. I'm just going to write the same thing. About the origin. Which I'm just getting this from this chart. It's the same thing. All right. What do you think x to the 10th is going to look like? Well, it is even. Once you determine that, we know all of our answers over here. So let's go ahead and graph it. Let's do y equals x to the 10th. Probably shouldn't have picked such a big number. It's going to be really skinny here. So it has that parabola shape. Let's bring up a table. Oh yeah, same kind of idea. We can't even graph 2 because it's 1,024. That one goes up really, really fast. So we know it's 0, 0, 1, 1, and negative 1, 1. I think that's what it was, right? Same kind of points, but that's about it. Just to show the direction, and then it just jumps up really fast, right? It's like really, really not the best graph, but just kind of get an idea of what it looks like. And then we're just going to use the table to remind ourselves what the answers are for even functions. So we know it has domain of all real numbers. The range is from 0 to infinity. So that's a bracket. And then what kind of symmetry does it have? This is the reflection over y-axis. Again, answers will always be the same. So really, if you just know this table, you'll be good. So the last thing I want to go over real quick is just kind of summarizing the odd and even functions. If f is an even, if f is odd, then the graph is symmetric with respect to the origin. So all the odd ones here would be, right, x cubed. You can keep going up. X to the 5th, x to the 7th. Doesn't matter how high you go, dot, dot, dot. They all have the same symmetry. And the last one here, if you have an even function, then it's symmetric with respect to the y-axis. So that would be x squared, x to the 4th, x to the 6th. You keep going, dot, dot, dot. So just don't remember the difference between the types of symmetry we have. The rest of it is just huddle, fill in the blanks, drawing some stuff. I might actually do a couple with you. You're doing some random sketches and just adding some numbers to see what they look like. You can do that in Desmos as well. But let me go over some things before we finish. So if you're good, you can just stop the video and do it on your own. But I'm going to go over some stuff as well. So if n is even, and what is the range of this? So if n was even, this number, the range is always, for even functions, is 0 to infinity. And the graph is in what quadrants? That's always in 1 and 2. Right? Think about a graph. If it's even, like x squared, you got this, 1 and 2. If n is odd, so if we have like a 3 here instead, think about that. The range is always all real numbers, and it's in quadrants 1 and 3. So this would be an example where it looks like this. Number 3, the graph of the quadratic function q, or q of x equals x squared plus 6x plus 4, intersects the x-axis in blank points. And the y-axis in how many points? Well, let's just go ahead and graph this real quick. Y equals x squared plus 4x plus 3, I think. Is that what it was? Oh, 6x plus 4. I was way off. 6x plus 4. There we go. And so it looks like it intersects in what points? In the y-axis. Points. So the x-axis hits twice. And the y-axis looks like it's going to hit it one time and go through at 4. So one time. So this is a little bit harder. 4 and 5, you can go ahead and do a basic sketch. These ones here, you're trying to figure out what kind of powers you have. I think the rest you can figure out yourself. For what values of n, if any, could the graph represent a power function of y equals x to the n? If it could not represent a power function, tell y. So this would be what values of n? This would be n is even. This would only be n is 1. So we're not. This is not a power function we've been talking about. So not a power function. We're only talking about really just numbers that are bigger than or equal to 2. This one would not be a power function. It's not the origin. So not a power function. Not the origin. My thing keeps messing up a little bit here. It's not the origin. And then lastly, this shape here gives you the odd ones. So n is odd. And that should be enough for you to finish up everything else for 7-1.